Hello Internet, my name is Quinn and this is Blondihacks. It's kind of a nuts and bolts episode on the DC generator project today because we've got a lot of little bits and bobs to make, but once those are all done, before the end of this video, we are gonna make juice! Here's where we left our little generator. It's got the end bells on it, bearings are installed, the rotor spins freely. Now let's see if we can add all the little bits needed to actually make electricity. I'm going to start with these binding posts. These are very, very small detail pieces, and they have quite an intricate shape. They have a ball feature in the middle and some other details. So I think the tornado might actually be the secret here. What I'm going to try is I've 3D printed the profile of that binding post. The drawing is 2x scale, mind you, and I'm going to use the tracing attachment on the tornado to create that shape in the binding post. This profile is very small, mind you, and I'm right at the limits of the resolution provided by the nose radius on the tornado. However, I think I can get away with this. You could also create a sharper tracing attachment nose, but then you'd have to grind a matching tool as well, but you could do it. I think I can get away with this though. I'm going to super glue my 3D printed template to a piece of aluminum that's just going to hold it in place on the bed of the tornado. The back edge of that template is the center line of the part, so I want to get that straight and aligned with the axis of the lathe, and give or take. This is an aesthetic shape that we're creating, so it doesn't have to be crazy accurate. And then I'll let that glue set. Before I attempt to cut the profile, I'm going to turn the stock down to the largest diameter that exists on the profile that we're going to be creating. I believe that's the ball detail and the flared base. Those two diameters are the largest. So I just did this freehand with the tornado again because absolute perfect precision doesn't matter here. Now with the tool touching the stock, I can align the tracing pointer with the widest part of the profile that I want to copy, either the base or the ball detail, as long as there's room laterally for this shape on the stock. And then I clamp that in place, and now we should be ready to go. If I did all that setup correctly, then I should now be able to simply make cuts at will with the tornado cutting tool, and the tracer pointer is going to limit me to wherever that 3D printed profile says the pointer should be stopping. And as you can see, as I nibble away at the material, that profile magically appears in the stock. It's really, really cool, actually. This tornado is amazing, and the tracer attachment is one of the funnest parts of it, I think. Look at that. This part also needs a threaded hole all the way down the center of it, which I can do without disturbing the tornado, so I'll do that now. You'll note that the shape is not a perfect match for the drawing. I am limited by, again, the minimum resolution that's set by the nose radius on the tracing pointer and the cutting tool of the tornado, and also 3D printing something that small on my 15-year-old FDM printer is kind of a fool's errand. It was just barely able to print something that small, so obviously the detail, the resolution of that print is also not great. However, I'm still really happy with the result. The final step then is to face down the flange at the bottom to the correct thickness. I arbitrarily set the profile on the tracing attachment kind of in the middle of the stock somewhere just to make sure I had room at both ends. I also gave it a little bit of a polish. When hand turning like this with the tornado, it's difficult to get really good surface finishes, so I usually need to do a little bit of emery work afterwards. The more you practice with the tornado, the better your surface finishes will get, however. Finally, I'm ready to part this thing off. I'm going to use the fret saw for this, so I have a minimal kerf because I didn't leave myself a lot of extra material there. And Yahtzee. Now the cool thing about this setup is I can pull out a little bit more stock, bring my tornado back in with the profile still glued to the table, and make another one, and both of those pieces will be exactly the same. For making 2 or 3 parts, this method really worked great. If I had to make, I don't know, 5 or 10 of these parts, then another way to do this would be to grind a profile tool. For a piece this small, especially in brass, you could grind this profile into a high-speed steel tool and push it right into the work and cut the whole thing in one shot. I actually demonstrated that technique on my PM1 steam engine for making tiny oil cups. I needed, I think, 8 of those on that engine, and I cut them with a profile tool. A profile tool like that, though, is a lot of work to grind and difficult to do correctly, so I think the tornado with a 3D printed profile was quicker and easier in this case. These binding posts need a cross hole drilled through them for the wiring. However, they're difficult to hold on to now because of their complex shape. However, the stock that I cut these posts from has a blind threaded hole in it It's excess distance from where I was tapping after the parts were parted off. So what I did is I cut the head off of a screw, threaded it into that hole, and now I have a mandrel upon which I can thread the binding posts. Because of the complex shape, I used the mandrel itself for edge finding to get centered up on Y, and then the shoulder on the mandrel gives me my X position, which is the same as the bottom surface of the binding post. That allows me to get the hole offset on X the correct distance. Then I center drill that and drill that through. Of course, I'm drilling right through the mandrel doing this, but that doesn't matter, it's sacrificial. And actually, I gotta say, that's a perfect cross hole right through a number 3 screw, so that was some pretty good edge finding there, I gotta say. And of course, this entire fixture repeats on every axis, so I thread the second post on there. I don't have to move anything on the mill, I can just immediately drill the second hole, and both of them will be in the correct spot. Now, these pieces are so small that I thought it would be a fun opportunity to try and up my metal finishing game a little bit. It's never been my strong point, but I decided to give them a buff on the old buffing wheel. And I gotta say, that really worked great. They came out very, very shiny. They don't look that shiny on camera, but in person, you can see your face in them, which is pretty neat. Well, I guess if your face is tiny. Next up is this lifting eye that goes on the top of the casting. This is a detail piece, but it's got a secret that you'll see in a minute. First, I want to verify the size of the hole that I drilled in that casting. It should match the drawing, but I never like to assume I did things properly in the past. Now, the cool thing about this piece is that it has a ball profile on the end. So we're going to need to make a sphere on the end of this piece. That'll be interesting. More on that in a second. I'm going to make the threaded stem first, however. Got the brass in there, face the end as is tradition, and turn it down to the diameter of the shoulder. The threaded section of this eye bolt has an accurate shoulder diameter and then a threaded area below that. The shoulder area ensures a snug and well-located fit in the hole, which you wouldn't get if it was just threaded all the way up. And that shoulder area is going to come in handy here in a minute for other reasons. Then the threaded area gets turned down a little bit further. You always need a clearance around threads. The major diameter is always a little bit smaller than the nominal diameter of the thread, especially when cutting that thread with a die, as we're going to be doing. If you have trouble getting the die to start, or it's really difficult to turn, probably means your stock was too large when you started, and you should turn a bit more off of it. Quick test fit on the casting, and that looks really good. All right, let's move on to the interesting part of this part, which is the sphere or ball end. So I need to flip it around, and I need to hold it this way. To do that, I'm going to take advantage of that shoulder cut. I'm going to use that as a superglue mandrel holding area. I found this rocket-shaped piece of aluminum in the scrap bin. I'll use this to create the mandrel just because it's fun. You could also use the threads for this, but threads are always less accurate, especially for concentricity in work holding than a shoulder is. So since I have the shoulder, I'm going to use it. The goal is to drill a hole that's very, very slightly larger than that shoulder so that the shoulder is a very close fit in there in order to maintain my concentricity. And that is, that's not going to do it. That is pretty sloppy. So let's Yahtzee that thing off of there and give it another shot. This time I went in with one size smaller drill. The nominal size drill cut a little bit over size on that previous operation, so that's why that didn't work very well. Okay, so one size down on the drill is a little bit too small, as would expect. So now I can go in with the nominal size drill, and since this drill has a pilot and it's doing less work, it should cut more accurately, and indeed it did. That is an excellent fit now. Now we're ready for super glue. Get a little bit on that shoulder area, and I'll fish that in there, give it a little twist as I go in to make sure that this super glue is coating everything. I don't have a lot of surface area there because it's a very small diameter, so I want to make sure this is a really good grip. And then I'll hold that in place, a little bit of pressure with the tailstock, and give that a full 15 minutes to cure. Don't want to skimp on this or it won't be strong enough. It'll break loose during your cut and disaster. To cut the ball end, I'm going to use the ball turning attachment on the Tornado once again. This is a really great little tool. The trick with it is it's difficult to set the radius exactly correct. It's really more designed for aesthetic ball turning than really accurate ball turning. But to start with, I cut and face down the excess stock so that it's the exact same length as the diameter of the ball feature that I want to create. And that is going to allow me to set up the Tornado's radius correctly. This is just the way that I do it. For another way to set the radius on this tool, I recommend checking out Mark Presling. He's got a system involving laser cut acrylic discs designed specifically for setting the turning radius of the tornado, and I think it's quite a bit more accurate than what I'm doing. What I do is just trial and error. I tweak the adjustment over and over until I find a position where the tool rests just on the surface on both the outer diameter and the end of the part with the pin in the same position. Once I do that, then I know my radius is going to be correct because that tool is going to end up on the surface on both of those dimensions. But again, Prezzo's way is better, so I will recommend you check out his channel for awesome tornado tips like that one. But here we go. Now it's time to turn the ball. All we have to do is move the tool back and forth, and as we get into the correct radius, the tool will click into that pin and stay there, and then we can finish out the ball. Unfortunately, I underestimated how much room I was going to need next to the chuck for the tornado tool, so I don't have the clearance required to get all the way under that ball. So I had to pull the mandrel out further, and I lost some concentricity doing that, so you can see a little bit of wobble in that part now, but it's not enough to lose any sleep over. I was able to finish out that spherical feature that way. I gotta say that worked really well. This tornado continues to impress. It's a very flexible tool. I'm gonna leave it glued into that mandrel now and take it over to the mill because we need to flatten out the two opposite surfaces of that ball to make it into an eye bolt. I've touched off on the top of the sphere, and I'm cutting down half the distance required to leave this thing at the correct thickness. Then, because I'm set up in a collet block, it's a simple matter to flip that block over, cut down to the same depth, and my flat surfaces will be correctly centered on the eye bolt, and the final thickness of the center of the eye bolt will be correct. Now I need to drill the hole through the center of the eye. I'm going to set up a machinist jack and some sacrificial scrap underneath it because there's probably going to be some deflection. It's sticking out quite a bit and it's a very thin part, so this will ensure that the hole ends up straight and on target because the part isn't deflecting while I do this. That came out pretty good, however, because I was again limited by the sharpness of the pointer on the tornado, I wasn't able to get the neck area below the sphere to be quite as small as it's supposed to be on the drawing. So I put it back in the lathe and I used a threading tool as a very sharp turning tool to get in there and tighten up that neck detail a little bit. It did leave some weird shoulder corner type things around the bottom of the ball, but I was able to blend those together with some needle filing. It's not a perfect solution, but it worked okay. And once again, I decided to give this thing a buff. Once again, that super glued mandrel was just the ticket for holding on to this thing. Buffing wheels are really quite terrifying. I consider them to be one of the more dangerous tools in the shop. The ferocity and unpredictability with which they will grab the part and pull it out of your hands is really quite startling. Anyway, we're done with that mandrel now, so I soaked it in acetone to break the glue. I normally use heat for this, but heat would discolor the part and damage the nicely polished surface that I just worked for. There we go. There is the final eye bolt. It's looking very shiny. Once again, you can see your tiny face in it, and that is a perfect fit. Very pleased with that little part. All right, we're in the short rows now. I need a magnetic spacer disc. This is an aluminum disc that sits inside the casting, and it actually threads onto that eye bolt and holds the permanent magnets inside the generator in position. My first facing cut on this stock left a little nubbin, which tells me that my tool height is too low. Facing stock is honestly one of the best ways to set your tool height correctly. And when this happens, it's a good opportunity to stop, fix your tool height, take another facing cut, and make sure that it's correct for all subsequent cuts. Especially for facing, because if you're going to be center drilling this part, that little nubbin can knock the center drill off course. But of course, it's always important for your tools to be on center in order for them to cut properly. I'll just zip through the rest of this part because there's nothing exciting about it. It's literally just a little aluminum disc with a threaded hole down the center. It's basically a nut, if you will, except that it's round. So it's more like a washer, a threaded washer, a washer nut, a washer nut, a nusher. Yeah, let's go with nusher. This is a nusher that I'm making, an aluminum nusher. In order to test this thing, we're going to need a belt of some sort. I found this O-ring here that should work. So now I need to make some sort of a pulley temporarily to drive it with this O-ring. I don't actually know what kind of belt I'm going to be using in my final steam plant to drive this thing. So for now, just to test this generator, I'll whip up a quick little O-ring belt pulley, using again some leftover aluminum and a round nose tool to create a round groove pulley. I just trial and error to the depth until it looked about right, like the belt's probably not going to pop out of there. A little bit over the center line of the O-ring is probably deep enough. I do want this pulley to be fairly small because we need to overdrive this generator quite a bit in order to get the RPM required to generate real volts. The shaft hole was center drilled undersize, and reamed for a really accurate fit on the shaft of this thing. Don't want any run out in that pulley. Quick test fit on the motor shaft, and oh my, that is an excellent, excellent fit. Boy, you gotta love reamers, they really are amazing. And then I'll part this off such that the groove is sort of centered. I don't know, doesn't matter. This is a throwaway part. Over to the mill now to drill and tap a little set screw hole in this to hold it onto the shaft. The generator shaft has a nice flat spot on it to hold a set screw without marring up the shaft, so this is perfect. The kit actually comes with a tiny set screw for this purpose that I didn't realize was in the kit, so I used a slightly larger one because it's what I had in my drawer, and I'll save the tiny set screw that came in the kit for when I make the final pulley, whatever that ends up being. The kit actually has drawings for a small scale flat belt pulley, which is of course what this would be driven with if it was a real generator of this era, but I again haven't decided exactly what I'm going to be driving this pulley with, or how I'm going to be driving it, what kind of belt, what speed, and so on. Alright, we should have enough parts now for some test assembly. I'm going to put the eye bolt down through there, and then I'll put the nusher in underneath, and I'm going to thread the eye bolt into the nusher, and the nusher is going to hold the permanent magnets at exactly one nusher distance apart, which is the exact place they need to sit in order to be up against the sides of the casting and not touch the rotor in the middle. The kit comes with these really cool curved permanent magnets that you slide in up against the nusher. Close contact with that nusher so that they're spaced exactly one nusher apart is key. I'm just trying to see how many times I can say nusher. Then the kit comes with this spring clip thing, which is actually quite sturdy. It requires pliers, at least for me, to squish that into position, and that spreads the bottom of the magnets outwards against the sides of the casting and up against that nusher at the top. That holds everything very securely in place. It's actually quite a nice design. It's very forgiving and very effective. The brushes need to be assembled now. The kit comes with all these little pieces for this. So there's these long brass screws that get threaded into one end of the brush. Then the kit comes with this insulating paper. It's sort of a wax or a plastic coated paper that we then cut to length and punch some holes in. And these get threaded over that screw in the brush and folded around the back of the brush and then cut to length. This paper insulates the brush from the end bell casting, which it's sitting very close to. This, of course, would ground out the brush and cause a short and cause cats and dogs living together chaos. The brushes can now be threaded into the end bell, and there's a little plastic insulator, again included in the kit, that goes around that screw, which keeps the screw from touching the end bell itself, which again would ground it out and cause a short. And then we push those screws through, and the binding posts attach on the outside of them. And that leaves enough thread inside the binding post for a little screw that goes on the outside to clamp the wire in place. It's a very simple design, very elegant. Every piece of the brush is doing 2 or 3 different jobs here, so it's quite efficient and quite a nice little assembly. That's roughly where the brushes are supposed to sit. The commutator will squish in between them, and you can see how that is all going to work, I think. Now, many of you noticed that in the previous video, my brushes were oriented horizontally, which is incorrect. The timing on that would have been wrong, and the generator would not have worked. They need to be oriented vertically, which is mentioned in the build notes, but I actually missed it. The drawing for the end bell, in my defense, shows the brushes being horizontal, so that's why I made that mistake. Luckily, my manufacturer was sufficiently accurate that I could rotate the end bell and everything still fit together, so bullet dodged on that one. After fishing the rotor in there and getting the brushes to sit nicely on the commutator, then we can put on the other end bell, and we're pretty much ready to go. It's getting pretty exciting now. Everything is assembled, so in principle, if we spin that shaft, electricity is going to come out. Then my little aluminum mock-up test pulley thing that I made can go on the other end. And see there's a nice flat spot on the shaft for the purpose. You never want to put a set screw for a pulley or anything else directly on a shaft, because the set screw will chew up the shaft, it'll raise a burr and make it very difficult to ever remove that pulley again. You see people do this all the time on old machinery, and it's a terrible situation because you can't get the pulleys off. And then when you do get the pulleys off, it chews up the shaft in the process. For the drive pulley, I found this fellow in the bins. This is a Delrin pulley that I actually made for this project here, which you may have seen. A couple of years ago, I drove the raffle drum at the Barzy Summer Bash with my PM1 steam engine. This was a lot of fun to do. We ran the engine most of the day on air because I didn't want to babysit the boiler all day, so you can see it running on air in these clips. But we did run it on steam for part of the day just to prove we could in fact have a steam-powered raffle drum at the Barzy Bash. Alright, so that same pulley I think should work really well for my little O-ring drive belt. Should be a nice overdrive on that. I have no idea if the ratio is correct, we're just winging it here, but found a piece of round bar, filed a flat spot on that for this pulley, and my hand drill will power that. Okay, let's get some wiring in there. I'll put a couple of wires in the electrical binding posts. I have no idea which one will be plus or minus, depends which way I spin the generator, of course. But I'll get my meter on there and let's see what happens. I put a little oil on those bearings as well. There's no facility for lubricating them, but you know, it's not really a big deal. DC motors this size run on dry bearings for years and they're fine. They're designed for it, but a little oil can't hurt either. All right, pretty exciting. Here goes nothing. Let's see if this thing makes electricity. Whoa, look at that. Look at that. How cool is that? At wide open on the drill, coincidentally, it makes exactly 12 volts, which is pretty much the maximum on this generator. So by sheer blind luck, I got the pulley ratio perfect on these two devices, but that is working extremely well, I have to say. Really, really cool. Man, metric horns of victory for that one. And sure, every 5th grade science class does this with bar magnets and paper clips, but it's still something really cool and magical about actual electricity coming out of a pile of scrap metal. Of course, by powering it with a drill, what I've really done is used electricity to make less electricity. But don't worry, cooler things are coming. Well, there we are now. This thing works, it makes electricity, it works exactly like it's supposed to. Could not be happier about that. This thing is not done, however. Of course, we're going to paint it, but I've also got more electrical shenanigans coming for this thing. So this is not the last video in this series. I'm going to do some really cool stuff I think you'll enjoy with the output of this generator. So stay tuned for that. But we know it makes volts. It's a really cool place to be on this project. Thank you very much for watching. Thanks to my patrons for making all of this content possible, and I will see you next time.